I'm able to thanks. All right, so for this session, we want to download the software that we'll be using and the program files. We'll use our git clone. And okay. And from your home directory. Should see README, examples, images, and test, and be able to run the command MPI run. And I'm going to choose 4 processes because I know this laptop has 4 cores. And I'm running a Python 3 program that's inside test. And I've encountered a few warnings on my machine. However, I have seen the expected output. So what you need to see is hello world from MPI rank and then a number. And there'll be a number ranging from 0 to 3, dependent on the number of processes you requested. So if you've managed to see something like that, I'd appreciate a thumbs up. And I see, Mark, you're here, and some of this might be familiar to you. So if you want to chime in at any point with a bit of information you think might be relevant for the rest of the attendees, you're more than welcome to. Great, thanks, Phil. Okay, well, let's get started then. So during this workshop, we're going to go through some of the fundamentals of the message passing interface, model of distributed memory parallel computing. And we're going to use the Python package MPI for Pi, which provides Python bindings to the MPI standard libraries. I'm going to use MPI for Pi to build up the structures and communication patterns that we need to implement a version of John Conway's Game of Life. And to start with, who's familiar with the Game of Life? Well, see something in chat. You played it a long time ago. Let's see if we're thinking about the same game. So, it's a game sort of without any players that was derived by the mathematician John Conway. And I'm just going to share, the Wikipedia here because it's got more information on it than I have in my head. And essentially with just a few simple rules, namely we have this grid, and in this grid we can have an alive cell or a dead cell, and we just have a few simple rules. So a cell which has fewer than 2 neighbors dies, as if by underpopulation. A cell that has exactly 2 or 3 neighbors lives on. And then a cell that has more than 3 dies, as if by overpopulation. And then any dead cell with exactly 3 live neighbors becomes a live cell. And this game has seen a lot of interest because this comparatively simple set of rules generates highly complex behavior. So I'll show you the end output of the code that we'll be developing over this session. Here we go. So this is the game of life playing out, starting with a sort of random distribution of live cells. We can see that these simple rules result in this really complex behavior. And in fact, like the behavior is quite complex. It's a chaotic system to the point where even though we know the rules of the game, they're fully specified, we can't ever really solve for the state of the game at more than a couple of iterations into the future. Just as a motivating force. Now this isn't, yeah, it wasn't that one, I think. So this isn't going to be a full-blown introduction to MPI because, well, MPI can be taught as a course unto itself, but it's going to be a tour of a lot of the fundamentals, and hopefully it'll provide a starting point for you to head out if you're interested in doing some more coding with MPI, to sort of head out, find resources, and start some self-learning. And if you would like to be pointed towards some resources that I found useful, please let me know and I'll send them through. So starting point of our discussion is going to be talking about how MPI approaches parallelism. So those who were at the parallel concepts talk last week might remember our discussion of distributed memory parallelism. And this is the model that MPI works in. So what we have is a scenario where we have an MPI communicator. Which I'm just going to denote as com. And within this communicator, we have a collection of processes which are all ID'd by a unique rank. So we would have the MPI process with rank 1 or rank 0. Then our second process would be rank 1. And then, all the way up to however many processes we've requested in our MPI communicator. So the highest rank will be rank n minus 1, where n is the size of our communicator. And within this communicator, ranks communicate to each other using message passing. So you'll have, say, rank 0 might have some data it needs to send. And then it'll send out a send request to rank, say, 1. And once that's received by rank 1 will then send that data. And unlike, say, shared memory parallelism with OpenMP, where we run a single program and that program encapsulates the threads of our parallelism, in MPI, what we're really doing is running separate programs which communicate to each other through MPI. So in our case, we're using Python. So what happens when we spin up an MPI communicator with 3 ranks is that we actually wind up with 3 copies of the Python interpreter, which each have their own independent namespace, so their own independent sets of the variables and data and so on. So this model is part of the reason why MPI is used so commonly in high performance computing and in supercomputing. So because we can write these programs where we could have, say, a single MPI process running per node, and then they're able to communicate over the network of the supercomputer. And in this model, we could also, say, have then finer grained parallelism at each node, say with OpenMP, that would be a hybrid mode of parallelism. So that handles, say, the local communication that MPI allows us to communicate over the network. So I think we'll just get now into actually doing some coding with MPI. And through that, we'll encounter a few more concepts and actually start putting together the structure that we need to implement our version of the game of life in parallel. And please let me know if you have any questions. This workshop assumes some familiarity with the Python package Numpy. If you haven't used it before and some of the syntax seems a little odd to you, please put your hand up and we can have an aside where we go through a few aspects of Numpy so you're able to follow along with the rest of the workshop. So we're going to start with just a hello world program. And when we're using MPI for Pi, our Python code will always contain the import statement, MPI for Pi, import MPI. And a detail that is being hidden from us when we perform this import statement is that the package MPI for Pi will actually initialize our MPI communicator. Whereas if we were using, say, C or Fortran, we would need a command in our code to explicitly initialize our communicator. So just it's a small detail to be aware of if you start looking at code in other languages. So some of the boilerplate is being taken care for us, but it's a minor detail. So MPI comes with this default communicator, and it's referred to as comworld, and it'll be the communicator that we are using. So mpi.comworld. And this is just the communicator that contains every process that we have created when we've executed our program. And as I said, each of those processes is identified by a rank, which we can access through either the com.rank attribute or using the getRank method. And then finally, we'll print out our hello world. And to run, now we're going to run our program. And as I said, with MPI, we're actually going to be creating multiple instances of our program. And this is done by our MPI implementation. So in my case, I'm using OpenMPI. And the command, this should be the same for you if you are running this on your personal computer. If not, you'll need to use an srun command from an allocated interactive session. So the command for me is mpi run, it's a -n, because I have 4 cores, and ideally you'd want to at maximum match the number of MPI processes to the number of physical processes on your computer. And I'll run it. And I see my hello worlds. But that's not particularly exciting. We've identified our communicator. We've established that we can get the rank of our communicators, but none of this involves any communication between the distinct processes. So this is where we get to the fundamental, almost, MPI directive, and this is the pair of directives, the send and receive directives. So I'm going to create another program called point to point. And just like before, I'm importing MPI for Pi. And that MPI object, I'm creating a variable to access the comworld communicator, getting my rank, and now let's do something. So we're going to say that if our rank has an ID of 0, let's create some data. In this case, we're going to create a Python dictionary. And then through the comworld communicator, access the send method. We're going to send our data to a rank with ID 1. So over at rank 1, we'll invoke a receive command from rank 0 and then print the data. And we see the dictionary printed to screen. So our A to B3, as expected, only once. So it's been, because it's just been printed at rank 1. So that's the sort of fundamental idea of MPI, is that we create copies of our program. They each do either a copy of the same work or a slightly different version of a greater sort of process. And then when we need to communicate, we use these directives to send and receive data. Now that example used Python dictionaries, and that's a functionality that is particular to MPI for Python. And I show that here because it's a particularly useful functionality. If we were using C or Fortran or some other compiled language, we wouldn't have access to such high level data types. So now we're actually going to go through a sending and receiving example that uses Numpy Arrays. And this is going to be the style of communication that we'll be using through the rest of the workshop. And it's the most efficient way to communicate data between MPI processes if using MPI for Pi. So we're going to head back to our point-to-point code. Say goodbye to our Python dictionary. And this time we'll create an array, a Numpy array. It's empty, 5 elements, data type. We're going to make it a double precision floating point number, and perform the same logic when it comes to the sending. So if our rank is equal to 0, we're going to populate the array with some data. So 0, 1, 5, and then send. So this time, we're going to be a little more specific about the kind of data that we're sending. And this syntax bears a closer resemblance to how MPI is used in C and Fortran. So hence, we'll be using it for the rest of the workshop because it's slightly more transferable. So we are in our first argument specifying our sending buffer. So it's going to be the data that is contained in array. And we're telling MPI for Pi that this is double precision data. So this is MPI.double. That's a particular data type that is supported by the MPI library. And just like before, we're specifying the destination. And if we're at rank 1, we're going to receive. data. And I don't see any bugs, so let's give that a crack. But there is a bug. We'll need to import Numpy. And there we go. We can see array at rank 1 and the values that we put into that array at rank 0. There are a few details to pay attention to here. Firstly, on line 8, so an array, I created this Numpy array, and Numpy arrays are distinct from Python lists. So they are an object that is of a fixed size. And we like using Numpy arrays essentially because they are able to sort of reserve for themselves sections of memory that are physically continuous in the memory of our computer, which means that if we want to do operations on that data, we can do that very quickly. They also support a lot of higher level sort of mathematical operations. Say if I wanted to sum this array by itself, I can simply write array is equal to array plus array. The next thing to note is this bracket colon bracket. So with Numpy, we're able to slice arrays. So if we wanted to select the second element through to the 5th, I can specify an index range. And importantly, if I just use that colon by itself, I'm explicitly referencing the full range of that array. And it means that when I use the linspace command to the right, that data is copied into the previously created Numpy array. Without this, the previous array object would be dereferenced, and we would essentially be creating a new object completely from scratch, which is a little memory inefficient. Next, this time around, our send and receive directives have a capital letter out the front. And that distinguishes these methods as being distinct from the Pythonic versions, where we're able to send just a generalized Python version over our communicator. When we're using the lowercase methods, Python is actually converting MPI for Pi will actually be converting the Python object into a binary format, and then sending that binary data over the communicator, and then converting it back to the original data type at the receiver, which is again another overhead in our code. With the capital letter versions that work with our Numpy arrays, it knows that it can rely on the data that is present in the Numpy array being of a particular type. So in this case, a double or float 64, so it's a double precision number. That way it can just take the bytes that it sees in one buffer and just send that without an additional conversion step. And so, it's not we're not just restricted though to sending between, one rank and another. One of the great things about MPI is it supports these collective directives, such as, well, we'll have a look at one of them now. It's called broadcast. So again, from MPI for Pi, import Pi, and import Numpy. Now communicator. Pull out the rank. And this time, if our rank is equal to 0, we're going to give it a value. So let's say just a scalar value, 10. Otherwise, it's set to none, and we'll call the broadcast method. So here we're using the Pythonic version of the broadcast directive to broadcast the variable value from root process 0. And make sure that I put an F at the front. It's an F string. Okay. And what we should see is that even though we have defined a value only at rank 0, none of them have it because it's not assigned. And we see that that value has been sent. So with that one command, we're able to broadcast same data to every other member of our communicator. Now I could continue on for the next 2 hours, systematically working my way through all of the most common MPI directives, and it'd be instructive, but in my opinion, perhaps not too interesting. So what we're going to do at this point is just think a little bit about how we would maybe go about parallelizing something like the game of life, and then just get to work putting together the communication structures that we need for that program. When we write MPI code or any sort of message passing code, we can kind of think of it as creating a kind of graph or program connectivity or topology, if you're a fan of topology. So like, if we have our rank 0 and then, a rank 1, and then let's say, third rank 2, and in our program, we are communicating primarily from 0 to 1, and then 1 to 2, and then 0 to 2. Our communication pattern is something like is a cycle graph. And this sort of visualization allows us to think about how data flows around and any bottlenecks that, we might incur. Say, for instance, rank 0 is, sending some, small amount of data, maybe like a combination of something. It's like a sequence. 0, we've got a 0, 1, and like 2. And then maybe 1 is responsible for giving us all of the combinations of 0, 1, and 2. So that'd be 0, 1, 2, and 0, 2, 1, and so on. We know that this is a pretty short process, whereas this will be much longer. And it means that whatever is going on at communicator 2, well, it'll probably spend a lot of time idle. And rank 0 will also spend a lot of time idle, so not really doing any parallel computation, because our rank 1 communicator is functioning as a bottleneck. So it's one of the useful things about thinking about it graphically. And if you're ever writing MPI code, it is really great to actually pull out a pen and pencil, doing now, and draw out these diagrams, as opposed to just going into it, typing furiously. It's much easier to run into a bottleneck or a communication sort of error that way. Now, in the case of our game of life, if we think about the game board, we have this grid. And there are a few natural ways we could divide this up. So we could assign, each communicator, say, each of the ranks could get a row. So we could have, rank 0 gets this row, rank 1 gets the one below, and then rank 2 gets the bottommost row. And then in that case, our connectivity, our communication topology looks something like a line graph. We could, instead as well, we could assign subsections of our game board to ranks in a two-dimensional grid. So in that case, we would have our rank 0, 1, 2, 3, 4, 5, 6, 7, and 8. And then our communication pattern would resemble a square lattice. There we are. Yep. That is 3 by 3. And MPI, in fact, has built in the ability to create communicators with a sort of a predefined topology. So as the Cartesian communicator, for instance. But we're not going to worry about them in this session. Instead, we will use point-to-point sending to implement this row-wise partitioning. So a line graph-like communication pattern that we've described in red over here. Yeah. So to set up this sort of communication pattern, we're going to have a scenario where we've got, here we'll consider 3 MPI communication with 3 processes. So we'll have our first rank. Excuse the spelling. So we'll have our first rank. Just going to have some subsection. Second rank. And third. And each of them will compute the rules for the game of life on their, their local partition of the sort of, global game board, which now doesn't necessarily exist as an actual, array, but is more of this a distributed concept. And think about the sort of data that each of the ranks needs from the rest of the communicator. Are there any, I'd like to actually ask, so what information will rank 0 need in order to compute the next iteration of the game? I'm going to either ask someone by name or someone can volunteer an answer. All right, Jake, you're in the hot seat. That's okay. Okay, all right, Alan.
Is it whether the surrounding cells being activated?
Yes, exactly. So I think by that, you mean like, which of the values on this boundary are either alive or dead. So the information that rank 0 needs from rank 1. Is that what you were referring to? If so, that is what I was looking for exactly. Thanks. So, for the most part, our ranks are able to just compute their local partition of the game independently. So, rank 0, we're going to have some cells that are alive. And unless they're up against a boundary, rank 1 doesn't need to know. But the moment we have, them at this sort of boundary edge of our partition, suddenly they need to, rank 0 needs to know whether or not there is an alive cell on this boundary. And this is a relatively good scenario for us, wanting to write a parallel program, because we can see that there's quite a lot of computation that needs to occur separate from this boundary. So in one iteration, we're only ever going to be communicating the data that is directly along the edge of a partition, and the rest of it is handled completely just in that local memory space. If we had some other scenario or some other game where every single value at rank 0 was needed by rank 1 to compute the next step, then we would be sending a large amount of data over our MPI communicator with each iteration, and it's likely that we would spend more time sending data than we would actually spend computing the next step. So rank 0 needs the top row from rank 1, rank 1 needs the top row, the bottom row from rank 0, and the top row from rank 2, and then rank 2 needs the top row from rank 1. We're going to now move on specifically to the workshop exercises. And I'd encourage you to, when we have a break at 11, to have a look at exercise 2.1. So it involves diagnosing a bug, a couple of bugs in some MPI code. But we'll just kind of get straight on to the goal of this workshop and move on to exercise 2.2, scatter. So for the next few exercises, we're just going to work with some abstracted data, but keeping in mind the sort of communication that we need to establish, the sort of pattern that we need to establish, we can set up all of those structures without really worrying about the rules of our game. So we'll import, just as before, MPI from MPI for Pi. And then Numpy. And we're going to write a program for, thanks, Melissa. It's important that you're able to see this. So we're going to write a program for 3 MPI processes. And we're in this code, we're just initializing the array at our root rank, which is, we've chosen to be 0. And we'll break from the examples a little bit. And instead of specifying a float type, specify just an integer type. Because we know ahead of time that to specify the game, we require a matrix of either zeros or ones, so just integers. So we can use an integer matrix with no loss of generality for the game's purpose. And then this line, we're just populating the array with some values. So for the ith row, I'm setting all of the columns equal to I. And our goal is going to be, it says, I'm finding my spot again. Our goal is to, at rank 0, to partition this matrix into a series of row slices, and then to send them to each of the other ranks. So we're creating that row-wise partitioning we just saw earlier. So the starting point of that will be to create a Python list. Going to call sendBuff, send buffers. And at rank 0, create a list of, well, a list of our partition slices. So this is now, we're going to use a Python single line for loop. I times number of rows I plus 1 times number of rows per process. Grab all of the columns. For I in range, the size of our communicator. I'm going to set, instead of n, let's use the more explanatory rows per process. So here, just as this, I think this might bear a little bit of explaining. If you've not seen Numpy array slicing. And also we're taking advantage of the fact that Python is zero indexed. So at if we think about this L list as having an index that references a particular rank, 0 times the number of rows per process, which is 3. So 0 times 3, that'll be 0 for rank 0. And then 1 times the rows per process will be 3. So in Python, it means we're taking a slice from the 0th row through to and including the 3rd row. So the row with index 2. Now we need a destination for our row slices. Call that my grid. And it'll start off as an empty array, which is going to be the size of the slice that we've created above. Now we have this additional variable num points. So this is going to be the columns. And also the rows of our global array. So let's say 9. And we're specifying a data type, integer, so a Numpy array of integers. So now we've got data that we want to send, a place to send that data, to receive that data at each of our ranks, and we actually call an MPI directive. And we're going to use a collective directive called scatter. So MPI MPI com scatter. And what scatter does is it takes an input array and it seeks to just divide up the input array evenly across all of the MPI communicators over the first sort of index of that list. Great question, Alan. Why would the number of columns for A be equal to size by n? Well, they wouldn't be. So they would be equal to the number of points, And let's make our code a little more robust. I'm going to do rows per process. Num points, we'll move them down below our rank and size, and actually calculate the number of rows per process from the size of our communicator. So we want it to be an integer, and we're going to just divide num points by the size. And set A, oh, and then of course A would be equal then to num points by num points. So for the scatter directive, we're defining first our sending buffer, and this only needs to be specified at the sending rank, which is 0. So and we'll use MPI integer as our sending type. And receive it into the grid. And specify that we are in fact scattering this data from the root process. And finally, to test this section of our code, let's print the sent data. So live coding MPI code isn't a trivial task, I think. So I'm almost certain that there's going to be a bug in this somewhere. So I hope everybody is managing to follow along and write some of this code. So as I sort out whatever it is I have mistyped here, we can all collectively fix our bugs and get our code running over the next minute or so. Test my code. Python. And you see that I have in fact counted a bug when I haven't redefined one instance of n, the n parameter. Awesome. So here we can see, I think, relatively clearly, the row-wise partitioning. So at rank 0, we've got row 0, row 1, row 2 with respect to the Python indexing. At rank 2, we have, or rank 1, we have 3, 4, 5, and then at rank 2, 6, 7, 8. And one of the things we can see here is that the ranks have an output in numerical order. And that's because once we start our processes up and running, those individual MPI processes aren't synchronized with each other unless we're performing a communication that demands that the processes stop before proceeding with the rest of the code. So in the program that we've written so far, the scatter directive is what we'd call it blocking. So when a process reaches the scatter, it will remain there until it has received data from the sender. Similarly, with the send and receive methods we saw earlier, when a rank executes a send command, it will remain at that point until the corresponding receiver has received that data and confirmed that the transfer is complete. So that's also another blocking form of communication. There are non-blocking forms of communication, so a non-blocking send and receive, but they should be used with a lot of care and forethought. All right, so now we have the data sent to each of the ranks. Let's start setting up the structures to perform that communication of the edgewise values. And this corresponds to example 2.3. So firstly, at our 0th rank, well, for everything with a rank greater than our 0th rank, we need an array in which we can receive the row above. So a Numpy empty array. So only need to store one row of the data, num points long. Data type will always be an integer. And then for all of the ranks that are less than the value of the bottommost rank, so that is the size of our communicator -1, remembering that our ranks are indexed from 0. We need an array to store the row below as it comes in. Next, now we can actually start sending some of the data around. So let's consider the case for a rank that is not the topmost or the bottommost rank in our communication communicator. So it'll need to receive from both the top and the bottom. So this is going to be the most generalized type of the most generalized scenario for our parallel program. So we'll say that if the rank is greater than 0 and also smaller than the highest numbered process. Let's execute a receive command. So we're going to receive from the row above. So we're specifying here that the source will be equal to the rank of the process that's communicating this code. So it's going to be this process's rank -1. And we're going to give it a tag. So this is like a unique idea for this particular sending like incident. So if we send something else from a rank to an identical rank, the tag is a way of differentiating between these two packets of data. And I know just from thinking about this ahead of time that I can get the unique tag if I take the rank -1, multiply that by 2, unique in the context of this code. And then once we've received our data, we'll do a send. So we're going to send our bottommost row of our partitioned game board. So -1 in Python indexes the last element. So the last row, all of the columns. MPI integer. And I'll give it tag ×2. So we can see here we've got the tag for the incoming data, and then at the sender, so without the -1, it's just we're using this rank ×2. Now, if I now then proceed with defining, say, the behavior of our rank 0, so our topmost rank here, and open with com send and the array we're going to send, so which will be the bottommost line of the local grid. Well, I can confirm that there will be an issue in the code. Any hazards as to the problem we've run into here? And so it's not really a syntactic problem. So it's not an error in the the way the code has been written in the language of the code, but it's actually more of a logical error. So say consider a scenario where we have two MPI processes. So a rank 1 and a rank 0. And how the ordering of these commands will play out. Or is there a logical error? Yep. Thanks, Alan. So, well, little subtlety, so a little almost like wrong in saying that there is an error, to be honest. This could be an error in that, if we are expecting to receive data from, our a rank that then is also expecting to receive. So if I wrote, if rank 0 was receiving, then we would hit a thing called a deadlock. So one communicator is requesting a data, the other communicator is on, the other rank is also requesting data, and then nothing happens. Like our code will actually just freeze, run forever, chew up all of your, core hours on Magnus or Topaz for however long you've requested, and then you'll have a look at your log file and you'll just see no output followed by a job step cancelled statement. However, in this case, because we're using these if statements, the way that's sort of set up, we know that rank 1 will execute this receive command. Rank 0 will pass over it. Rank 0 will then send the data to rank 1, so referencing this earlier receive command seen in the code. And then, rank 1 will go on to send its data to wherever else it needs to go. So, while certainly I think makes it a little easier because it matches the sort of partitioning scheme, if we put rank 0 at the top here, in terms of the actual logic of our code, everything is exactly equivalent. So I think at this point, we're going to take a 5-minute break and get up, have a stretch. If you're at your desk, maybe try to implement some more of these communication patterns. So, how would we send what is the sending pattern we would need to see from rank, the bottommost rank with respect to, the rank just above it. So that would be an if statement. If rank is equal to size -1. And we'll need to include a receive, that's a little statement, a method, and also a send. Great. See. So now we've all had a chance to stretch our legs and, acknowledge that it's quite a nice sunny day. We'll continue along implementing our communication, this row-wise partitioning communication pattern. So we have defined the behavior we want to see at rank 0 with respect to, so rank 0 is going to be sending the bottommost row of its local partition to the rank below, and then ranks in between rank 0 and our highest numbered rank going to be sending receiving the row above. So that's the bottommost row in the rank with the next highest number, and then sending their bottommost rank to the rank below. So this is communication paths this way. That's what we're sort of considering. And then for the highest valued rank, it will be performing a receive operation. So taking again that row above, destination, so the source, and so the rank above, rank -1, using our system of tags to identify this particular send and receive pair. Great. And for the send, now this is where we're going to start sending up. So the send from the bottommost row will be with respect to, will be the topmost row of the local grid. So row 0, all of the columns. You can see that as I'm typing this, I am making use of auto-completion in my text editor to avoid having to write MPI integer out over and over again. And because this is the sender, the tag will be rank times 2 plus 1. So this is the unique tags for the sends going up. And now we'll consider, so we're moving up. Now let's consider all of the ranks in the middle. And to save my fingers, I know it'll look something like this block of code here, so I'm copying that. Pasting that down. And just modify this where we need to. So instead of row above, we're receiving the row below. And instead of receiving from the rank above us, we're receiving from the rank below. And the tag is just a little different. And now, of course, what we're sending. So we're sending now the topmost row. Destination will be the rank above. And that slightly different tag just to distinguish between sends going up from sends going down. And in doing that, I noticed that there's a little typo there. So that should be, because it's a send operation, we're talking about a destination instead of a source. And finally, we want to specify the behavior for a topmost rank. And I could put this under the same if statement at the top, but for ease of readability, place that below, and instead of a send, we're performing a receive. And we're receiving the row below us. The source is going to be 1. And tag and there we have it. So that is a single complete communication pass for one iteration of our game. And I see there's a message in chat. So should it also be rank +1? For which of the for desks up above when traveling down? Yes. That's correct.
Wait, no, sorry, I didn't mean that one. I
Oh,
think
no.
it was
Wait.
above that one.
Above this one?
Yeah, the one just above where
So
the send just above that one, sorry. Yeah, that one there.
This one, right.
Yeah.
So we're sending the bottommost grid. Yes, so it has to be the one below. Thanks.
Yep,
Nice
no
and
problem.
spotted. Cheers. And now that that has been done, we'll just print for all of our ranks. This will be a little bit messy, but it should give us a sense as to whether or not it's behaving as expected. So we'll have the rank and we want to print the we want to print the row above, and let's also print the row below. For if the rank is greater than 0, or the rank is less in size -1, because for our edge cases, we do not have row above or row below defined. Else, if our rank is 0, we'll just print the row below. And then if it's our bottommost we'll print, just copy that, just print the row above. And as before, I've written quite a lot without testing our code, so highly likely that I will encounter a bug. It's one of those things where the probability just tends to 1 as you write more lines. So as I fix any oversights in my code here, I hope you're able to do the same. If you encounter any errors that seem mysterious, please either post them in the chat or feel free to shout out. Great. So yeah, there we can see line 88. I've got my colon. And I've got on my aboves and belows back to front, line 89. I think I have.
Also, with the printing at the bottom, you wrote if rank is greater than 0 or rank is less than size -1. I think it should be and.
Yes.
Otherwise, it'll trigger both.
Exactly.
Yep.
Thank you.
No worries.
It's a big help. Perfect. Yeah, so we can take a look at our data at rank 0, our data at rank 2. So the bottommost row of rank 0 is populated with 2s. We would expect for at rank 1, then we'd expect row above to be populated with 2s, which we see. Great. And then at rank 1, so the row below 6s, so we'd take a look at rank 2. Yep, so the topmost row on rank 2, there are 6s. So and that's the row below rank 1. You can see now we've succeeded in passing the values backwards and forwards between our various partitions. Now that we're sending data, in the, the pattern that we're sort of looking for, we can now start to build out our, boilerplate code into an actual, simulation of the game of life. And this sort of process, as you're figuring out the structure, your communication structure, and then establishing code to implement that structure. It's a mode of, I think, MPI code development that I find to be quite useful. By just defining a easy to pass, easy to understand source sort of matrix. So our matrix A, which just contains, again, the numbers by row. We're able to use print statements to debug a small version of our MPI program. Whereas if we were using a matrix of ones and zeros, as will be the case in an implementation of of our game code, well, it's much harder for a human being to figure that out. You don't want to have to be sitting there with your finger the screen, kind of just like matching up cells, trying to see if the communication pattern is correct. There are also there's a software does exist as well to help with the debugging of MPI code, but especially when you're starting out and trying to just set up the core of your program, really kind of trying to reduce it down to the essentials is very helpful. But now we've seen that they're working, let's implement a single iteration of the game. And to do that, we'll start by defining the game kernel. So the code that's going to execute at each of the MPI ranks on their local partition of the global game board. So we'll just define this right at the top code, and we'll call this function game step. It's going to take an array in as an argument. Call that the local partition. And now we need to think about how we're going to implement this step. So reviewing, just as a refresher on the rules of the game. So for each of the cells in our game board, we need to count the number of neighbors. So instead of drawing individual squares, let's just grid up something a little larger. So if this center cell is a cell we're considering, we're going to be checking whether or not each of these cells, its neighbors, is either equal to 1 or 0. And depending on the sum of all of its neighbors, it'll either live onto the next iteration or die. And the criteria we have is, any cell with fewer than 2 neighbors dies, any cell with 2 or 3 neighbors continues on, any cell with more than 3 neighbors dies, but any dead cell with exactly 3 cells comes alive. So those are all of our game rules. And I could implement this by creating a couple nested if statements that loop through each of the squares in my grid, so each entry in my Numpy array. But that operation, you'd quickly wind up with a horrible nest of if statements, and we also have to think about edge cases. For instance, what would I have to do in my code if I'm actually on a boundary? So in that case, the cell over here doesn't exist, so my code will need to factor that in. Sort of avoid having to worry about all of those details, we're going to use a slightly less intuitive, but definitely a more efficient approach to calculating the total number of neighbors. And we're going to perform a convolution over our game board. Those of you who are doing machine learning may have encountered the concept of a convolutional neural network. And this mathematical operation that we're going to go through now occurs in those networks. So that's how we actually get, it's how we kind of take a high dimensional or a large image and reduce that to a lower dimensional output in our neural network, but that's an aside. What we're going to do is we're going to create this thing called a kernel. The kernel will contain ones, zero in the center, and we're going to move this kernel over the game board, multiplying the elements in our kernel with the overlapping element on the game grid, and then taking the sum of this kernel. And in doing so, we arrive at a value for the number of neighbors. So say if we had this scenario, we move this, our kernel over here, we superimpose it over the cells, we'll get 1, 0, 1, plus 0, plus 1, plus 0, plus 0, plus 0, plus 1, plus 0, plus 0, for a final number of neighbors equal to 3. And in that case, this cell would live on to the next iteration. And another motivating factor for using this kernel method is that the package SciPy, very common Python package, has a signals processing module, which contains a convolution method. So we can make use of code that someone else has already written to implement our game logic. So from SciPy, importing the signal module. and defining our kernel. So we're creating a Numpy array of ones, 3 by 3 elements. That contains integers. And of course, always want to put an A at the end. And the centermost element, the center of our kernel, is 0. And compute our neighbors using this kernel and the convolve method of the signal module. So we're acting on our local partition using the kernel we've defined above. And there are a few different modes of convolution to reproduce that summing behavior I just described. The mode that we want is same. You could also say perform a convolution and return the average. And now I can write a condensed, much simpler for loop and series of if statements to create the game board in the next iteration. So local partition old. So I can reference this as I update the next version of our game board. And using the Numpy's copy method. So this means that I'm explicitly requesting that local partition old be a completely new version of the array local partition, as opposed to a local partition old being a variable that points to a copy, like the same, so it points to the same array as local partition. So something that you might have encountered, or a lot of people encounter when they're new to Python, is writing something like A is equal to 2, B is equal to A, B, adding 1 to B, and then like printing A, and then seeing that A actually is equal to 3, because in saying B equals A, we've created a second reference to the data that is stored in variable A. So hence the need for that copy statement. And in a loop for I in range, local partition, getting the shape attribute, the first dimension of our input array. And for J, in range, local partition, shape, taking the second element, the shape attribute of our input array. If the previous value that ij is alive, so equal to 1, or we'll implement the rules for the alive cells. So if I and j is less than 2, then our local partition ij is going to be equal to 0. If the neighbors ij are greater than 3, then we'll also set it to 0. And then, if not, it's left alone. But if it's not equal to 1, in which case it's a dead cell, if the number of neighbors ij is equal to 3, we birth an alive cell. And we conclude our game kernel by returning the local partition, and we're also going to return the number of alive elements. So moving down to the bottom of our code, let's call the kernel at the corresponding ranks. So in the most general case, if our rank is greater than 0 and also less than our highest rank, what we want to do is actually pass to our kernel our local partition with the row above and the row below concatenated. So there's going to make use of another useful function, this time from Numpy. So I can say I want the output array. So, so we want the next step, and the number that are alive. These are our returns. I'm going to call the function GameStep and use this Python. Actually, not entirely sure what the term is for calling it's almost like a decorator, the R underscore and then a list. So if either Jordan or Melissa or someone else in the chat knows the correct terminology, feel free to shout out. But Numpy has this handy little R method or ability where we can use this R underscore and then pass a list row above my grid, so it's that local partition, and row below, and that R underscore will perform the concatenation that we're looking at, as long as the size or the dimensionality of all of the arrays is consistent, so that they're all 2D arrays. To satisfy that condition, we're going to reshape the row below and row above arrays to make them into two-dimensional arrays with explicitly two-dimensional arrays, but a two-dimensional array with a single row. So our row below, we're going to define its shape as being equal to 1 and the number of points, and the row above likewise. And the array we're going to receive as next step is actually going to have the topmost and bottommost arrays appended or concatenated, and we want to, just keep our local partition. So we'll use Numpy array slicing. So mygrid is going to be equal to that next step array, but leaving out the top and bottom. And now for our edge cases. So rank 0 and rank size -1. The situation is much the same. So I'll move through things. Well, I was going to say faster, but then I could feel myself getting ready to just like let loose a flurry of awful typos. So let's say at a measured but consistent pace. So reshaping our row below at rank 0, calling our game step function, and assigning the output so in this case, we're only dropping off the bottom row of the output. I'm going to copy and modify this for the bottommost rank. So rank size -1, which will have an row above. And of course, for rank 0, we don't have a row above. And for size -1, we don't have a row below. And in this case, we're going to drop off the topmost. And while it doesn't affect the logic of the code, I think that the phrase local partition is somewhat misleading, because it's not the local partition necessarily that the game step kernel is receiving. It's the local partition concatenated with any of the received arrays. So I'm going to perform a search and replace with them. In your own code, if you've used the phrase local partition, it's okay to keep on using it, or you can use a search and replace in your, however that is done with the text editor that you're using. So I can do what we call local partition. Just call it game board. Great. And we'll modify, while we're down here, let's modify our code, our print statements, to print out migrid at each rank. And implement, and now for our rank A, let's create something that's, that actually obeys the rules. So at the moment, we've got values ranging from 0 to the number of ranks. We want an initialized array that contains only ones and zeros. And there are, in fact, a few interesting starting configurations for the game, just as an aside, where you can wind up with these really kind of cool looking repeating patterns, and there are names for the various objects, such as glider that are produced by those initial conditions. So if you're playing around with the code afterwards, I'd encourage you to have a look at that and try setting up some of these initial conditions. But for our purposes, we'll just invite the stochasticity, the randomness of the universe into our lives, and we'll generate we'll initialize our game board as a random configuration of zeros and ones. So A is equal to, from the Numpy random module, going to use the choice method, and we're choosing from a small Numpy array that I'm explicitly defining here, so which contains integers. Zero and one. And the size of our array of random choices is num points, and I think I'll just go with the probability of choosing either of the elements. We're going to weight them. So we've got a higher chance of getting a 0. Just to prove the readability of the code, let's put some things on the run line. The inputs, there we go. So now going to test one iteration of the game. Fingers crossed, and fix your bugs along with me. Okay. There is an error on line 39. My random choice. Ah, yes. Thanks, Jerome. The first of these should be 0.7. And then our probabilities sum to 1, and the universe is happy, and quantum mechanics is consistent because probability is conserved. And I've also encountered an error with me not importing the R underscore. From Numpy import. Run the test again. And now there's an error in the kernel. That's fine. It's saying that my game board is an integer. Which implies to me that somewhere I'm passing the wrong argument to GameStat. So I'm use Vim to just search for GameStat. Shouldn't be it, but that's just detail. Prevent just creating a actually, no, sorry, I'm gonna leave that because we have already created another array in the GameStat kernel. And it looks like, to me, it looks like I'm calling that with the correct arguments in each instance. Ah, there we go. There I am taking the game board with all of its information, and I'm just discarding it, dereferencing it, and pointing it towards the integer 1, which is exactly what we do not want to do. And rerunning my code. Brilliant. So now it's a little harder to tell whether or not the code is doing exactly what we want it to do because we've put some real data in. But I see arrays of ones and zeros. I don't see any incredibly large or small numbers, which could result from me sending or receiving data with the wrong specification. So maybe receiving, I'm sending an integer, but I'm looking for a double, and then it's interpreting that input, the received data as a double, and spitting out, kind of garbage essentially. So I'm not seeing any errors like that. It looks like things are communicating nicely. But one step isn't that exciting. ideally we run this out over a series of iterations so we can actually see the game evolve and play out. And here we're going to make use of MPI's broadcast operation and the gather operation to firstly impose a stopping criteria on our simulation and also gather the results of our parallel code and visualize it using matplotlib. So say goodbye to our exploratory print statements. And this code, so this code is going to be inside of a while loop. Our communication, single iteration communication. Our initial scatter, that only occurs once, so that'll be outside of the loop. Remove that other exploratory print statement. And gonna just implement a few little niceties. So we're gonna put this in a while loop, and we want this to continue while the number of iterations is going to be less than the maximum number of iterations that we'll allow. So the number of iterations is going to start off at 0, and we'll set for our maximum number of iterations, say 100. And we're going to make use of the count of alive cells that we're getting from the kernel, game kernel. So let's say, yep, total alive. Let's set that at the size. Initially, we'll start off with it as being just the size of the game board. And we'll implement a stopping criteria where if the total number of alive cells drops down to 0, we'll halt the simulation regardless of whether or not we have exceeded the number of maximum iterations. Because at that point, our program is just going to keep sending, zeros to and fro, creating no new information until it hits the number of maximum iterations. And for a program of the size that we're working with now, that's not so important. But if, for instance, we were maybe trying to simulate this at a much larger scale on something like a Magnus, you really want to make sure that you're using your core hours to do good work. So it's good to have these sort of convergence checks in your parallel code. So let's say that if the total number of alive cells is equal to 0, we're going to break out of our while loop. And now we're moving down to the bottom of the code. And we'll use the Mpi Gather method. So com is being called at all of the ranks. Gather and the send buffer is going to be the number of alive cells. It's an integer. And we're going to receive it into an array that we'll call, let's say, the populations at each of the ranks. So populations, which will also be of MPI integer. And we're collecting that all to the root process. So destination, also root equal to 0. And so for this to work, we need, so we've got an alive defined, but we need a populations array. And that populations array, so it's going to receive that value, the nalive value from each rank. So it needs to have a length that is equal to the size of our communicator. So moving back up to the top of the code, here's something else we need to define. So if the rank is equal to 0, we'll have our on our populations array, it's going to be a Numpy array, well, an empty Numpy array of a size that's equal to the size of our communicator, and it contains integers. Otherwise, for everywhere else in the communicator, this variable is none. Points to none. And if we don't define populations at all of the ranks, irrespective of whether or not it's actually being used as a target, when we execute this gather command, because it's being executed by every process in our communicator at ranks other than 0, they'll see this here populations variable and we'll receive an error. Basically, just populations is undefined. So we have to point it to something, so it needs to be defined, but it doesn't need to be a Numpy array at any of the ranks other than the receiver of the gather operation. So in this case, rank 0. And with these gathered information, we will perform some operations at our root rank, so rank 0. And we just want to get the total alive. Let's take the sum. And maybe use this as a point to print out a little bit of feedback as we're running our simulation. So got to say the iteration. And that was called numiter, numiter, and the alive cells. Total alive. And I'm going to use this option, the print function in NumPy called flush. And what that does is we're requesting that the output of our print statement isn't buffered. So by buffer, that means you collect some amount of data or amount of output to print, and then once it reaches a particular threshold, or when the execution of the program, the process halts, then that output to standard out, or the output carries on to standard out, so to our terminal. But what we want to really ensure is that as we're performing each iteration, that we're really getting a live update. So by setting flush equal to true, every time we trigger this print statement, the print statement is immediately sent to standard out. It's probably a bit of an inefficient way to monitor the process of the program. If you think about it, like if we collected up all of those print statements and then performed that single output at the end, that's a lower number of calls essentially to the standard out. But if our MPI program encountered a communication error that was blocking, we may have a scenario where we never see any output because it builds up in the buffer, the program halts, and then we just never see any information. So we won't be able to easily identify the iteration at which point the program broke down. And now we have this information, so the total alive. We're going to broadcast the total alive. So now we're using the sort of Pythonic variant of broadcast. To send total alive from rank 0 to all of the other arrays. And at the end of our loop, we're going to increment iterations. And so if we look up now, the start of a while loop, see that statement, if total alive is equal to 0, the simulation will terminate. And I'm going to test my code. Let's fix the bugs. Let's fix the bugs together. And the next step will be to use matplotlib to visualize the game.
I think your gather at the bottom is inside an if statement that it's not meant to be inside of.
Ah, thanks, John. Let's see. Yes. Yes, you're correct. Thanks. So there we can see this like surprisingly large number for our grid size. So, what's happening there is we're performing this gather operation, and it's a gathering with respect to one rank for a start, and then also it's kind of just like referencing an empty buffer, but really this empty buffer, so the populations array. NumPy's just set aside a piece of data, some data in our RAM, and said this will be where we contain integers associated with this particular array, but it doesn't do anything to initialize the data that was already present. So whatever collections of 1 or 0s that happen to be in that location, they still exist. So when we're performing that gather statement, it's actually taking that kind of like garbage data from memory, and then interpreting that as an integer. You can see here we've got this value which is much larger than the total size of our grid. So that's sort of behavior, this sort of like unexpected numerical results. It's like a key signature of there being a bug in your MPI Python code. Hey, and that is, much closer to what we expect. So we're starting off with 43 alive cells, and as the game progresses, we're reaching 0. We won't always, because it's possible for the game to arrive at a sort of non-terminating chaotic configuration, but there are a smaller number of those configurations than there are configurations that'll perish. So let's put some matplotlib code into our loop so we can visualize all of our work. Turn these bits into something that the human eye is able to understand. So using matplotlib, and heading to the bottom of the code, just before we increase the iteration counter, because that feels right to me. I feel like the iteration should be over when we've done all of our work. We're going to introduce a gather operation. So the game grid. Which we'll have to define are actually, in interests of time, 5 minutes. Going to use the easier to define but less efficient Pythonic gather method. So this is another version of the method we can see above with the populations array. So com lowercase gather. Now we're going to gather my grid at each of the ranks to the root process. And we're at the root process, so rank is equal to 0. We're going to take this data, going to call it the, let's see, a game iteration. Going to turn it into a Numpy array. Because above we have taken the Numpy array, mygrid, and then gathered that into a Python list of Numpy arrays. So we're going to convert that into a three-dimensional Numpy array. And then reshape it into a two-dimensional array, which is consistent with the configuration of our 2D game board. So game iteration, reshape, and use the matplotlib function matShow, matrix show, to visualize the game board. I'm going to output it to a directory. So I'm going to output this to a results directory and just number each of the outputs. As the output file name, we'll just use the iteration number. And so matplotlib doesn't complain, and we don't use up a lot of memory by opening up a whole bunch of plots and over the course of the simulation. I'm going to close that. So where our final step is to gather together the local partitions. Sorry, gather together the local partitions, and then at the rank that is responsible for gathering, so our root rank being 0, we are changing that Python list into a Numpy array. And because it's a list of two-dimensional Numpy arrays, the same size, what we're creating is a three-dimensional Numpy array. We're then reshaping that three-dimensional array into a 2D array. So we're reclaiming the dimensions of the global game board and visualizing the game board using the matplotlib method and matShow, matrix show. I'm going to make a results directory and execute the code. And fix some bugs. So I've got my game iteration. Yep. Making that into a Numpy array.
You spelt reshape without the S.
Thank you, Joe.
And also after that, it complains about, I think, using matShow wrong or something. I'm not sure about that.
Well, let's see.
Yep.
Okay. Oh, that is because I have sort of garbled together two lines of code. So we should be saving a figure after we have created the plot by passing our game iteration to the matShow method. Great. Okay, what I'm going to do now is head to the results. Oh, I can see some plots. And move them to where I can find them easily on my Windows file system. Of course, I have to specify the thing that it is that I'm wanting to move. And let's take a look. Great. And here we can see the simulation output. And if we really wanted, we could try to figure out if the rules are being obeyed from frame to, well, from iteration to iteration. But we can see something like what we would expect. So it's a starting configuration. Second step. And it eventually dies off to our empty game board. So it seems like we've managed to successfully implement the game of life in parallel. And that we're a little bit over our 12:30 endpoint. I don't want to keep everybody from projects and appointments that I'm sure you all have. But with this code, just want to point out a few details. If you want to have a bit more of a play with it yourself. Firstly, we're able to increase the size of our game board by changing the number of points. However, it has to be, because of the way we've partitioned it, it has to be a number of points that is divided, that is has to be a number of points that can be evenly divided by the size of our MPI communicator. So if I wanted to continue to use 4, I could maybe increase this to a grid size of 40. And we can change the number of maximum iterations, of course, or the stopping condition. And for those who have ImageMagick installed, which I think might be available in Homebrew, and I know it is available on Ubuntu. So if you're using your own personal machine, so this or a container that contains ImageMagick, so you might not be able to do this at all on Magnus, and you shouldn't try to install ImageMagick onto Magnus. In the examples folder of the code, you can see another implementation of the game of life. Under this results folder, I've included this animate shell script that'll take the input, the output plots and bring them together into that animated GIF that we saw at the start of the workshop. Yeah, so thanks for joining me for this workshop. I hope that learned something new. and you have a bit of a starting point for using MPI in your own code, or if you decide that it is something you want in your projects, that you kind of know the terminology and where to start looking. It's been a interesting and a challenging topic to talk about in a single session. So I'm very keen to hear feedback and how we could develop this workshop. The aim is to demonstrate something that is a little bit interesting. So, the game of life, and it's something which we might very well actually want to parallelize in this fashion. So we want to demonstrate something useful while also not getting too into the weeds or just spending 3 hours listing MPI directives. So if we've failed on any of those parts, we've gone a little too deep, please let me know. Or if you want to learn more, please send me a message, and I'd love to have a chat and send through some more material. Thanks.